We'll be starting here in a minute or two.
Get put together the right way. Very good.
We'll be starting here in a few moments. We'll be starting here in a moment or two. Okay, I'm going to go ahead and share my screen with you. And today, we are going to finish with the Explosion Lab and the Impulse Lab. And so the goal is so that at the end of the meeting today, you will have all of your answers for both of those labs, lab responses, and you'll be able to turn them in. And I'd like you to turn them in before the next Zoom meeting, which will be on Thursday for us at 10:55. So as long as I get them before then, that's fine. As far as turning them in, I'm going to kind of leave that up to you. For instance, some people I think probably have access to a printer, and maybe they printed out the lab sheet, the response, and just because they prefer to do it by hand, that's fine. Realize that that's yours and none of your partners, because I know that you're not sitting together collaborating. So that's only yours. However, if you would like to collaborate with your partners and just simply turn in one set of whiteboards with all your polished answers on there, that's fine. Just make sure that on that it has all of your names on the actual board, like where the graphical mathematical models are. And please put all those whiteboards in one folder. So that it's a little bit easier, doesn't clog up my email. I'm going to stop sharing for just a second. At the very bottom of your screen, do you see there's kind of a reactions with a smiley face? If you click on that, there's like a clapping hands if you really think there's a great presentation. But more than that, there's a thumbs up. Can you guys do the thumbs up right now that you understand that labs do? Okay, that way I know you hear that.
How to do the thumbs up?
Thumbs up, it's at the bottom. There's a reactions. Bryant, do you see the thumbs up at the bottom?
Oh, you need to go full screen. Okay.
So Bryant, at the very bottom, there's a reactions kind of, for me, it's at the bottom, kind of to the right, a little bit off center. and it's a little smiley face with a plus. And if you click on that, there's a thumbs up.
Is it in like the chat or something?
No, it's off.
Hey, Brian, you gotta go full screen on Zoom, and then next
Oh,
row.
gotcha. 1 sec. Is it right? 1 sec.
It's like a little smiley
I mean, I
face.
pressed this thumbs up.
Huh. Okay.
Huh.
Okay, every
That's
once in a
weird.
while, maybe verbally, you're just going to say, yeah, I totally get it. Okay.
Okay.
All right. All right. So now I'm going to go back to sharing my screen with you. And so what we're going to be doing is we're going to be whiteboarding the rest of the lab. So you should have those whiteboards from last week. And for the, let's start off with the explosion lab first. Do you guys mind muting yourself? Thanks. So we're going to start with the explosion lab, and I don't have the graphical and mathematical models written on here, but if you remember, this was kind of a, it was an inverse graph. It was negative inverse, and so the mathematical model, though, we got was velocity of the red divided by velocity of the blue equaled negative, and like I said, it was negative inverse graph, so it would have been the mass of the blue, can't spell, divided by the mass of the red. And we rewrote this so that we didn't have to deal with fractions. And so we had mass of the red times the velocity of the red equals the mass of the blue. Actually, forgot my negative. Negative mass of the blue, can't spell again, times the velocity of the blue. And we define this quantity of mass times velocity, we call that momentum. P equals mass times velocity. And it happens to be a vector quantity because velocity is a vector quantity. And so the reason why there was that negative symbol on there is because they were going in opposite directions. So that's kind of the models that we ended up having for this. So actually for this lab, I think for these questions, I just kind of want to do together. So for this first one, again, here's the consensus mathematical model. If both of those cars had the exact same mass, let's see if I can draw it so you can kind of remember it. There was a red car and there was a blue car. Let's say they have the exact same mass. In class, the way they would have shot away from one another is in one of the cars, there would have been a little spring mechanism, a little plunger. So I'm going to make that black. And this was the beginning, and then we triggered it. And what happened is then the red one shoots off one direction, the blue one shoots off in the other direction. The question is, if both the cars had the exact same mass, how would you expect their final velocities to compare for one another or to one another? Can you unmute yourself and kind of shout it out? How would you expect them to compare?
To be
Say it again.
to be the same.
Yeah. So their speeds would be the same. Their speeds would be the same, but they're in opposite directions, right? So kind of same magnitude, but opposite directions. So can I get a thumbs up from you? Do you guys agree with that? Yeah. Okay.
Yeah.
Good. Probably the important question is why? Why would you expect that to be true? Anybody? You're right, it is true, but why?
Mass times velocity and then mass times velocity. Since they have the same masses, they have to have the same velocity.
Okay, and probably because of Newton's third law, they would have the same force on them, right? So same force, They have the same force on them, same mass, so therefore they would have the same speed. Makes sense to me? Good. Now, the truth is, if we did this lab in class, are you guys able to hear me? Can you thumbs up if you can hear me? You're all good? Can you guys hear me? Okay. I wasn't sure if I was breaking up. If you did this lab in class, the truth is that there might be in fact, it usually happens that one of the velocities isn't quite the same as the other velocity. So in other words, or isn't the same magnitude. So in other words, let's say the blue car is a little bit slower. Can you think of any real world phenomena that would make it so they didn't have the exact same speed, even though they have the same mass? Any ideas? Anything in the lab that maybe would cause them not to have the same speed?
Air resistance.
Okay, so yeah, some kind of resistant thing. Usually it's not air resistance, but maybe some friction. Maybe the wheels of the blue car have more friction than the red car. Can anybody think of anything with the track? Not so much with the wheels or friction.
What if like the track on the blue car was like rougher, so that had more friction?
Right, so more friction, that's a possibility. Can anybody think of anything just with the track though, with no friction, something else?
If they were a different distance from each other,
Different distance.
the center of the explosion, I mean.
Oh, okay, I see. Well, it's kind of hard to imagine this because we didn't actually get to play with these cars, but they're actually the same distance from the explosion because the thing that explodes away is actually like a spring inside of one of the cars. So the distances would actually be the same. But what happens sometimes is this track isn't exactly level. And so that's another thing that would possibly affect the speeds a little bit. So thumbs up if that makes sense to you.
Yeah.
Yeah, okay. All right, so that's that question. So you got the answers there. Okay, let's go on to number 19. In the two-fragment explosion that results when a gun is fired, explain why the bullet acquires a high speed while why the gun does not. Let me see if I can draw a picture here. Let's see, gun, picture, cartoon. Let's see. Ooh, there we go. We'll pick that one. All right, so here's this gun, and it shoots out a bullet. So here's the bullet being shot out. So in this explosion, just like the explosions of the two cars exploding away from one another, the bullet is shot out one direction, usually a very high speed. And the gun, believe it or not, actually, if you never shot a gun, you probably wouldn't know this, but the gun actually also moves backwards in the other direction. So we call this a recoil velocity. But usually the velocity of the bullet is much bigger than the recoil velocity of the gun. So can you guys come up with a reason? Why is it that the bullet is so much faster than the gun?
The velocity is inversely related with the mass.
Right, yeah. I probably should have copied that model again. So let me put that model here. So yeah, that totally makes sense to me. This bullet has a very small inertia, a very small laziness factor. And so if it has the same force as the gun, if it has very little inertia, very little laziness, it's probably going to end up going a lot faster, and it does. I have a question for you. Well, let's say you're a gun manufacturer and you're trying to design, new and crazy guns. And let's say you make a gun that shoots a huge bullet, better to take care of the bad guys. And the mass of the bullet is the same mass as the gun. So let's see if I can try to make it look like it has the same mass. There we go. So there it is. So my question is, how would the speed of the bullet compare to the speed of the gun?
The same.
The same.
Yeah, it'd be the same,
right?
Yeah, it'd be the same. So probably not a good idea to design this gun because the recoil velocity, you might end up losing your hand. So probably a bad design. Okay. All right, good. And then let's look at the last one here. The truth is, the last one here, I don't really want you to answer on your lab response because you weren't in class, you weren't able to see this, so it doesn't really make a whole lot of sense here. So let's just skip this one. Don't do this one. So when you turn in your lab response, you won't do number 20. Thumbs up if you got that.
Got it.
Got it, okay. All right, okay. All right, now we're moving on to the Impulsive lab. So we're done with these. And again, I didn't draw in the graph this time, but I hope that you remember it from last time and you have it in your notes. It was a direct relationship. In fact, the relationship was that the impulse, I'm using the letter J for impulse, is equal to the change in momentum, where momentum is mv. So change in anything is final minus initial. Now, if the force is constant for the impulse, it would be equal to force times t. So if it's constant force, it doesn't ever change, it's just F times t. And so in this case, if it's constant force, it'd be F times t equals mvf minus mvi. So that's going to be the mathematical model we're using for these problems. Stop me if anybody has any questions. So for number 20, you're going to be using this mathematical model here to answer this question. So what I'd like to do is give you about 2 or 3 minutes to answer it. And then what I would like to do is just the same way that I'm sharing my screen, I'm hoping that somebody will share their screen. And again, the faster we get this whiteboarded, the faster we're done. So I'm going to stop sharing and give you some time to work on number 20.
I gotta pull it up.
Dan, can we just give people a few seconds here to work on it just a little bit, and then I'll let you pull it up, okay? Sorry about that.
Oh, no, you're right, my fault. I don't know if I have it done. I just thought that we were all pulling it.
Oh, okay. All right. Oh, I didn't get a chance. I forgot to ask you guys, are you guys doing okay at home? Everybody all right? Thumbs up if you are, or they ought to have a sad face emoji. Yeah, okay. Hey, you can change the color of your thumb. I forget where exactly I found that at, but it's kind of cool. So. Just this is off topic. I don't know if anybody's getting cabin fever. I know I was. I don't know if you've ever been to, it's called Channel Lakes State Park. It's not very far from here. I'd say it's maybe 40-minute drive, but it's just this really big park. There's not a lot of people there, and lots of woods and lakes and stuff you can walk around. It was totally free when we went this weekend, so I don't know if you've ever been, but I totally recommend it. It's really cool.
Oh, the parks aren't closed?
It wasn't this weekend. I don't know if it's closed now, but it was totally open. Now you can't camp there, but we could walk around. We walked around for a couple hours. It's really kind of cool. Is that park closed now?
All the state parks are open and free, but you can't camp or do anything other than go to trails.
If you're really cooped up and you're wanting to get out, I totally recommend Chain of Lakes. It's really kind of nice. In fact, it's hard to believe that's actually Indiana. It's kind of neat. Okay, somebody want to share their screen with us? So at the very bottom, there's a green share screen. So you click on that, and then a pop-up will come up, and you just click the blue share. So anybody wants to do it, the faster we get it done, the faster we're done with this. So pretend this is like whiteboarding, where, you know, we all whiteboard for a little bit, and then somebody presents it. Okay, Jaden's sharing.
Cool. Can you see that?
Yeah, perfect. Yeah, so just kind of walk us through, how did you solve it?
Well, I used the equations with the mass times final velocity minus initial equals the impulse. So then I did one. I don't know why, but I always factor out the mass. I just think it's easier for some reason. So then I have 1.5 times 0 minus 10, and you get negative 15.
Yeah, and then probably I probably only have one critique. All your math, by the way, no critiques. It's absolutely perfect. At the very end, since it's vector, you kind of have to explain what that negative means, and you did. I would just simply write the answer as 15 kilograms times meters per second to the left. So other than that, totally perfect. By the way, factoring out the mass, absolutely right. But I would like to let you know that on an AP test, sometimes it's the mass that changes. Like for instance, a rocket. So imagine you have this rocket taking off. It's got thrust upward, and because it's shooting gas and stuff out, its mass is changing, and so the mass is actually changing, and the velocity is changing. So you'd have MVF minus MVI, and you could have different masses. So that's a possibility.
Gotcha.
Yeah.
Okay.
So very, very nice. Everybody give, how about a clapping hands? There's a clapping hands thing on there for Jaden there at the bottom. Yay, clap hands, yay. Nice. All right, so Jaden, if you can, I think there's a way to stop sharing your screen then. Yeah, perfect.
There we go.
Okay, so I'm gonna go ahead and share my screen again. That was awesome. Okay, so that was number 20. Sorry, I had to move this out of the way. Okay, number 21. Again, we're going to be using that same model here. So I'm going to copy it. So number 21 looks like this. I know I skipped those first true false. We're coming back to it at the very end after we do some practice of the mathematical ones. I think they'll make more sense. So for number 21, it wants to know, now that we know what that change of momentum is, that impulse in number 20, now it wants you to calculate what the force is. So I'm going to give you a few minutes to go ahead and calculate the force. So I'm going to stop sharing, take a few minutes to do the calculation, and then somebody will present. Okay.
What was question? 21? Sorry.
Yes, number 21. Yep.
Okay.
Okay, does anybody want to share their screen with us? Again, you just go at the bottom, you click on share screen, and then a pop-up will come up and choose the blue button that says share screen. So anybody can do it. Faster we get it done, then we're all done. And I would like somebody else. So Jaden, don't do it again. I appreciate you guys, Jaden, doing that for the last one, but I really want I want other people to kind of get the hang of how to use this program. Okay, this is Dan. Okay, and just kind of walk us through, if you could, Dan, how you solved it. Dan, can you talk? I'm not hearing you.
Oh yeah, sorry, I had it muted.
Oh.
So isn't this the F net is equal to delta P over delta T?
Yeah.
And then
Yeah.
solve for that, and that's the force.
Yeah, there you go. So you just simply took the force times the time equals the change of momentum that we just found in the previous one, which was 15, and you get 150. Now, the only thing I have to say is that we have, because force is a vector, we have to say the direction. And
So it'd be
so,
negative.
well, yeah, it's a negative, but then let's look at what number 20, if you remember, it says that it was moving to the right and it's slowing down. So if it's moving to the right, it slows down. Which direction is that force?
To the left.
Yeah, there you go. So 150 newtons to the left. Perfect. And then at the bottom, Dan, if you could just, or wherever it's at, just stop sharing. Thanks. All right, so now I'm going to share my screen, and the next problem we're looking at is number 22. And I forgot to bring the equation, the mathematical model. We're going to be using the same mathematical model. And so let me give you about 2 or 3 minutes, 5 minutes if you need it, to go ahead and solve the problem. Right, so I'll stop sharing. Somebody want to share their whiteboard? Again, at the bottom, somebody different. So Jaden, Dan, I appreciate it. Just kind of lay back and we'll have somebody else present. At the very bottom, there's a little green share your screen. And then a pop-up will come up when you click that, and just choose the blue share screen. It's okay. This is just like whiteboarding. It's okay to be wrong. It's not a big deal. And Krishna, I appreciate your doing this. So can you walk us through, Krishna, how you went ahead and solved this then? You might have to unmute yourself. I can't hear you.
Yeah, so
Okay.
I did force times time equals MVF minus MVI, and then I just plugged in the numbers, and I got 4.8 meters.
Cool. Everything looks great. I just want to make one small critique. We have to be careful in this section because there's vectors involved. And so your calculation is absolutely correct. But we need to have a direction. So what direction would that be?
To the right. I mean, to the left.
To the left, right? Because if you look at this, it says it starts at rest, and then the force is to the left. So that means this velocity vector is going to have to be to the left. There it is, 4.8 meters per second to the left. Perfect. Awesome. Any questions on that? Okay, Christian, if you could then stop sharing. Perfect. All right, I'm going to share my screen now. All right, let me copy this before I forget it. And 23. So 23, similar idea. So this one we have, well, I'll let you go ahead and read it through it. And you're trying to figure out this funny looking symbol here. That means the integration FD, the integration of the force DT, FDT. That's really the impulse. So it wants you to figure out what the impulse is. So let me stop sharing, give you a few minutes to solve it, and then somebody will present.
Mr. Linfesti,
Yes.
for this one, would there be a vector, even though it doesn't state a like a direction it's going?
Yeah, and the problem with this one, you're absolutely right. I think this is Daniel, right? Is this Daniel?
Yeah.
Yeah. The problem with this one is it doesn't say left, right, east, west, or anything. So that means you might have to use a negative in your answer or a positive or whatever is appropriate. So this is one of those cases where you might use a negative.
Okay.
Does somebody want to share there or somebody different that hasn't shared yet? Malia, all right. And Malia, you may have to unmute yourself.
Okay,
Okay, just walk us through how you solved it.
so I found the initial one, which was mass times velocity 1.5 times 10, and then the
Okay.
final, which was the mass times the new one, which was minus 10. And then I just did the final minus the initial to get negative 30. So then it'd be negative 30.
Yep,
is the
perfect.
impulse.
So it's negative 30, and the units would be kilograms times meters per second. Perfect. So yeah, as Daniel was saying here, in this case, that it doesn't say what the direction is, so you just leave the negative 30 there. Perfect. Thank you very much, Malia. If you can stop sharing then. Okay, and then I will share. Let's give for all our participants, and I forgot to do this earlier. How about a reaction of a clapping there? Everybody that's shared. Hey, look at that. That's nice. Awesome. Okay, so now let me go ahead and share. Let's see. All right. So number 24. And I forgot to copy. Okay, so actually before we do 24, I'm going to come back to number 23 and kind of draw a picture here. So one of the conceptual problems that sometimes students encounter with this one is, because this is kind of strange if you think about it, this problem 23. Because at first you might be thinking, well, the impulse here, the change of momentum, it goes from 10 in one direction to 10 in the other direction, the impulse is going to be 0. So here we have this cart that's, let's say it's moving to the right. And let's say it hits a bumper, a spring. Let's see if I can draw a spring. I don't know if I can. I'll do the best I can. So let's say there's this spring here that it's going to bump into right before it hits this wall over here. And here's the wall. And then, of course, it's going to bounce back in the opposite after it hits the wall, after it hits the spring will cause it to slow down, energy stored as elastic, and then it shoots back in the other direction. We'll say there's no dissipative losses, and so that means the speed would be the same going in and coming out, okay? Kind of like in this problem. And most people would look at it and go, oh, you know, that's a nice cushioned collision. So that's really nice, and that's going to be a very small collision. So it's not going to be any painful whatsoever. And so that means the impulse, the force would be kind of small. So that leads us into number 24. Because for number 23, you're thinking, oh, the impulse should be small. But as Malia just showed us, it's not small. It's not 0. It's actually pretty good size. It's actually, it's like doubled. It's going to be negative 30 kilograms times meters per second. And that leads us into number 24. Johnny says that bumper cars are safe because the impulse experienced by an occupant is less than that experienced by someone hitting an object and coming to a stop. In other words, it's safer to bounce because the impulse is less. What do you think? So what do you think? Do you think Johnny is correct or not? So you might have to unmute yourself. Correct or incorrect?
Incorrect.
Are we all agree? Incorrect?
Yes.
Yeah.
Yeah.
Yeah. So the reason for it is Johnny is thinking for, I'm going to go back to this one. Johnny is thinking this equation. Actually, I've got the equation. I don't need to do that. He's thinking with this equation here that this velocity here is 10. It's shooting back at 10 meters per second. And this initial velocity is 10. And I'm pointing this out, and I'm using the word Johnny because I don't want to use any of your names. And I'm going to tell you right now, some of you will make this mistake, and I don't want you to make the mistake. I really recommend that you draw a picture so that you can see, oh, it changed directions. One of these has to be negative. And so Johnny made this mistake by forgetting the negative, and so he's going to get 0. That's not true. One of them's negative, and so now it's actually going to be big. This impulse is actually going to be big. So bouncing doesn't make the impulse smaller, it actually makes it bigger. That's why in cars, they give you a headrest so that your head doesn't bounce back and forth. Because when it bounces back and forth, that would be a bigger impulse. They call that whiplash. So any questions for that one? Give me a thumbs up if you think you understand it so you can answer it on the lab response. Okay, we're all right? So again, Johnny's mistake was he forgot that it's a vector quantity and one of them's negative. Okay, so the last one we were going to do is we're going to do the true false. And so there's all these questions here, and so I would like to give you a couple minutes to answer all 5 of them, and then we'll go over somebody's whiteboard. So I'll stop sharing. And that will be it. And whenever somebody thinks they have the answers and they want somebody different, somebody wants to share their whiteboard, feel free to take control of the screen. Again, it's at the bottom. There's a little green arrow that says share screen in Zoom. And then a little pop-up will come up and you choose the blue button. And this will be the last one. So the quicker we get it done, we're all done. It looks like a nice day out there. Has anybody been outside?
It's nice, but it's cold.
Did you go for a walk or?
No, I just checked the weather this morning.
Oh, okay.
Yeah, it says 36 or 37.
That's the temperature, 36 or 37?
Yeah.
Wow.
Holy
That's
cow.
cold.
Yeah, it is. Golly.
High is a 42.
What?
And we have snow. We have snow tomorrow.
Nuh-uh.
Apparently, 70% chance.
Jeez.
Yeah.
So somebody new want to share their screen? Quicker we get it shared, faster we're out of here. So again, it's okay to be wrong. It's not a big deal, right? This is just like whiteboarding in a lab. If you get it wrong, that's all right. Now we know the answers before we turn it in. Okay, well, we're still waiting. Then I'll go ahead and share my screen just so we can kind of take care of the other stuff. So I'm not going to do it. Somebody else is going to do that. But I want to go back to the. Oh, I didn't put a link here. That's okay. I will put a link here. The only other thing to do, like I said, those labs are due by next. Well, I'm looking at the wrong thing. That's why. The labs are due by next Thursday. But the only other thing to do today then is to take this attendance quiz, which is just over this whiteboarding stuff that we've done, these practice problems kind of. So you'll click on this attendance quiz, and I can't remember how many questions there were. I think there was 4 or 5. Yeah, 5 questions. You'll need this code, and the code is lowercase y, t, uppercase N, C, C, lowercase e, k, hashtag, and then lowercase v. So you might want to write that down. And that has to be done by midnight tonight. So it's over the stuff we just whiteboarded basically. So it should be super simple.
Could you repeat the code?
Yeah, it's lowercase y as in yak, t as in Thomas, then uppercase N is Nancy, C as in cat, C as in cat, and then lowercase e as in elephant, K as in kayak, hashtag, and then lowercase v is in valley.
Cool, thank you.
Yep.
Mr. Wenfesty?
Yeah.
So is J and FT, I mean, integral of FDT, are they the same thing?
Yeah, so J stands for impulse. Impulse is defined as the area underneath the force time graph. So therefore, J, the impulse, is equal to the integral of F dt. And impulses cause changes in momentum. So J is also equal to MVF minus MVI. So it's really kind of neat. There's more than one way to find impulse. You can either do the integral of F dt, or if it's constant force, you can do force times time to find impulse. Or if you don't know force, you don't know time, you can calculate the change in momentum. So MVF minus MVI, that's also impulse.
Okay, thank you.
Yep.
I can share my screen if you want me to, but I don't know how accurate they are.
Hey, that's all right. So Adam, yeah, at the very bottom, just share your screen, hit the share, the green share, and then when a pop-up comes up, hit the blue share button. Perfect.
Can you see it?
Yep, there it is. And so the very first one there for number 15, momentum is a vector quantity. I agree. If you agree with that, thumbs up. Other people.
Thumbs up.
Yeah,
Yes,
I give it. Yeah, it has direction, right? So it's mass times velocity. So it's, yeah, that's a vector. And then number 16, change in momentum is a scalar quantity. Well, if momentum's a vector quantity, change in momentum has to be vector, right? Thumbs up if you agree.
Yep.
Yep, so it's not scalar, so I agree, it has to be false. Then number 17, it says impulse is a scalar quantity. So realize the impulse is the same thing as change in momentum. So really 16 and 17 are really the same thing. So do you agree with number 17? Do you agree with him? Thumbs up if you agree. Everybody's responding.
Yes.
Yes, yeah, okay, I agree, yeah. And then number 18, it says impulse is the same thing as momentum. Well, impulse is the same thing as change in momentum, but impulse is not the same thing as momentum. So thumbs up if you agree with Adam there. It's false. Thumbs up. Yep.
Yep.
And 19, we just kind of answered that too. Thumbs up for that one. Let's give Adam a hand and bottom. Yay, reaction. Yay.
Go Adam.
All right, so if you can stop sharing your screen, thank you. And I've already explained that you're going to turn in the labs by Thursday at 10:55 and just do the attendance week. That's it. So see you later. Bye.
Awesome. Thank you.
Yep.
See ya. Have a good
Bye.
one.
You too. Bye.